of quantum mechanics. We give the last seminar talk in this experimental seminar on the foundations of quantum.
All right, thanks Dr. Zilberger for inviting me, and thank you for Minja for letting me talk. First of all, I'm not a foremost expert, so I'm just beginning student of this all. And I found this subject very fascinating. That's why I've been studying this with Shelley and Michael for the past few years. And I hope that this topic can be interesting to other people outside people who work in mathematical physics and philosophy of science, because I think that quantum theory seems to be very central to our scientific worldview these days. But a lot of that seems to be very confusing and mysterious, as they presented in, say, physics classes and popular press. So I hope to do some work today to clarify some misunderstandings, and also trying to give some further references about what to read if you're interested in this topic. Okay. So, well, thank you all for coming, and I hope that this talk will be very brief, but I hope to, give you some pointers about what the problems is and what the solutions are. To me, it seems to me that the quantum measurement problem is at the heart of the mysteries of quantum mechanics. And I want to illustrate the measurement problem through a series of 3 very simple thought experiments. And we can see that with some precise mathematical framework, we understand this a bit more, but still the measurement problem is not solved until we go beyond what is presented in textbook quantum mechanics. So that's one of the goals today, is to see one particular solution to the measurement problem, namely Bowman mechanics. Okay, so the goal for a lot of foundation quantum mechanics is to find a clear, precise mathematical physical theory of the world. And the vision we have is based on, say, the classical theory of particles and fields developed by Newton, Lagrange, Hamilton, and so on, in which there's a very clear theory, a theory which not only laws of motion, like F equals ma, but also an ontology of what there is in the world. So in the classical world, we have tables and chairs that are composed of, say, small particles, and planets are composed of smaller parts and particles and so on. And there are forces between small parts, and they have interactions, and they'll create motion by Hamiltonian formalism or, say, Lagrange formalism. And that is the explanation, a clear picture of what the world is about. And the ontology picture seems to be missing in much presentation of quantum mechanics. In quantum mechanics, we are often, face the question, what's really going on in this simple experiment? Can we say something definite and precise about the, say, the apparatus and the system being measured, and interaction between them, and so on? And it's very hard because quantum mechanics itself seems to be lacking in both mathematical and conceptual tools to do that. Okay. So I want to go through some examples. The first one is the single slit experiment. So in this one, okay. So we'll start with this one as a simplifying thought experiment, but it's very illustrative for later calculations and thinking through this. So in this experiment, we have what is called electron gun. Basically, you have some battery here. You have a wire system, and 2 sides, the opposite sides of the battery, and they're shooting electrons one by one on some technologies. So you have electrons shooting emitting from this electron gun, and we expect and we see this pattern on the screen. Basically, you have many flashes, one by one on the screen. And as you go through this many times, you'll see a pattern forming. There are more particles landing here, where is the center of the slit, and fewer here. But in general, you see this bell-shaped pattern distribution. And this is empirical distribution of, say, doing experiments thousands of times. Now, this seems to be, well within our expectations. And classically, we could, for example, shoot bullets through this one. And suppose bullets are, randomly distributed across, say, these parts. They can be different directions, but if you have a reliable mechanism, it's most likely to be in this part. Sometimes be moving around, conducted by this edge to here and so on. But most of the bullets are going to arrive in this part, this way. So it seems like nothing surprising has happened yet. Until we have two slits. So in this experiment, we have the same electron gun, shooting electrons one by one, so it can be further away. So it's not always hitting here. It's far away, and if these two are close enough and also small enough, then we see something else. But given this single slit experiment, we might expect that, for example, if the electron goes through the slit one by one and go through one of them at a time, say the upper slit and the lower slit. So electron, one go through the upper slit, then you might have something around here, right? And electron two go through a lower slit, you might have something around here. Suppose you have hundreds of electrons going through this and this. You may have half of them going through the upper slit, half of them going through the lower slit by the symmetry of the experiment. And you might see maybe something like that happening, the two bell-shaped curves. Maybe you have this, where you center around this slit, and you have this, center around this slit. And together, if both are open, you might expect to see something like this, where this is the addition of the two bell curves. And
Dip in the middle.
The dip in the middle. Good. Like this. But in any case, it's continuous, right? It's continuous distribution. You just simply add this two bell curves. Okay. But that's not what actually happens in the lab or in this thought experiment. What actually happens if you do the experiment is something like this. You have a discrete pattern. Where some part has many, many particles hidden on the screen. And some other parts get almost no electrons hitting the screen. So instead of a continuous distribution, you have a discrete distribution. And you might ask yourself, what explains this phenomenon? And what explains the kind of difference between this picture and this picture? By applying the assumption that particles go through one of the slits, and when they go to this one, when this is open, doesn't affect the trajectory that it happens. So that's the question you will see presented in, say, Feynman's lectures and other textbooks we see. Seem to be a very big mystery of quantum mechanics. And some people even say this is the only mystery, as Feynman would say. So, well, if you think about this long enough, you realize maybe electrons are not quite like particles. So maybe this indicates some kind of wavy things going on, some kind of interference patterns going on. Because if you imagine this not an electron gun, but some kind of water waves here. And the water waves being kind of agitated here, you're producing sound waves going through this one, almost like a plane wave going through this one, and then have diffraction from the two slits, right? And there will be some parts when you hit the screen that have constructive interference, and some parts that have destructive interference. So in that case, we might have a water wave forming on this part of the screen. You have some more water here, maybe less, up and down here, more up and down here, less up and down here. But you know, the wave phenomena is going to be recalling for extra ingredients or mathematical representations. The particle will still to be have definite location, say Q, at this point. But it's a wave phenomena. Maybe we need something else. So what is representing the wave here in quantum mechanics for the electrons is going to be something called a wave function. For a single particle, it's going to be a function from R3, three-dimensional space. In this case, maybe R2, because we have just two-dimensional notation, to some complex numbers. And these numbers can be, you know, R e to the I theta. So you have the modulo and the phase of the complex numbers. And when, say, you have two parts of the waves, you have, say, psi 1 and psi 2. And if this evolve in time by some linear evolution, we say that more later, then we'll find some parts of the wave will be interfering to be constructive, some parts of which will be destructive. That correspond to the values in which, say, you know, you have on a complex plane two vectors, one in which at one point it might be aligned in the same direction, it's the same phase. Then you have constructive interference. So other places you have, say, out of phase completely by pi. Then you'll be destructive interference. You have complete zero, cancels out. So we have a wave function here that seems to explain a little bit of the interference patterns on the screen. Okay, so you have, say, R1, e I theta 1, and R2, e I theta 2. So if theta 1 is, say, theta 2 minus pi, then it will be destructive, and you would get 0 here. If theta 1 is same direction as theta 2, then it will be constructive, to be adding more stuff. So this places will be constructive, and this places will be destructive interference. Okay. So the first step is to add this wave function to represent the system, the electron system. And you might ask, what is the exact equation of change for the wave function? And that was given by Schrodinger's equation, which is the type of equations of this form. Some change of the wave function in time, given by some operator times the wave function. You can take one wave to another wave function. But this one is going, it's going to take one wave function and then producing some kind of velocity, different changes to the wave function. And for, say, non-relativistic quantum system, you have this product, which is, say, the gradient squares of the velocity. You have h bar, which is the Planck constant, and mk is the mass of the electron with v potential, right? So in this case, we can think of this as saying, given by the construction, potential is given by, say, maybe it's infinite here, or this is going to be completely blocking the wave function. So this is going to entail this important property of the change of wave function, namely that
h bar squared.
Sorry.
And why do you have a k index up there?
Yeah. Yeah, single wave function. Yeah, single particle wave function. Then the important feature of this equation is that it is linear. That is, if say psi 1 index by t, solution to this equation, then n psi 2 index by t, solution to this equation. Then the linear combination of the two will be another solution to this equation. So, for example, so constant alpha plus beta psi 2 will be another solution to this equation. Okay. Now, we know from the single slit experiment, we have the following features. If we close this slit, just let this part to be open, then we're going to have the change to be, you know, like giving you something like a diffraction pattern on the screen, like this. And you let this open and this closed, we're going to have the diffraction kind of like this. So if you like both slits be open, then the prediction, the Schrodinger equation, is that the two, psi 1, psi 2 is going to add in a linear way. And the evolution is going to be, preserving the independence of two ways. So what you have is going to be psi 1 plus psi 2 at all times. Now, since psi 1 and psi 2 are complex number functions, we're going to have, at some points, they're going to be in phase, be constructive, and at some point they're going to be out of phase, to be destructive. So at some point there'll be, adding more to the amplitude, some parts will be adding little to the amplitude be 0. Okay. Right. So if this is, the entire description system, we might have the problem. That is, when we do a single experiment, we see just one flash on the screen, not kind of mushy phenomena, not kind of like entirety of flashes, but just one flash on the screen. And already you can see that just by the wave function plus the Schrodinger equation, we don't quite know how to explain this precise, discrete kind of pattern on the screen one by one. Although the prediction of quantum mechanics is going to add more things to it. It's not only the wave function plus the Schrodinger equation, but some other rules for extracting predictions, namely collapse the wave function and one-rule probabilities. But in any case, I want to leave this as a kind of indicator for something missing here. Now, to go to the third experiment, we're going to add something else here. So in this third experiment, it's called the double slit with some monitor in the middle. So electrons are attracted to protons with a positive charge. So if we have a proton here with positive charge, suppose we have some kind of device here. If you move this way, there's a flash here. Move this way, there's a flash here. So suppose we have an electron coming out of the electron gun one by one. Now, with this monitor, we're going to see exactly which way, or which slit the electron goes through. Suppose we have a perfect correlation in a proton. That is, exactly if you go through this one, you will 100% of the time come to this one. And that means we're going to have perfect monitoring of the which way information of the electron. So suppose we have detection here, then we know it's coming here, probably something arriving here. Okay. With this introduced in the experiment, we assume that maybe we'll still have interference pattern on the swing, but just we'll have more measurement of the experiment. Maybe we can know if you come this way, you will first flash here. But no, what actually happens with additional device here added is that you have simply the addition of two bell-shaped curves. Exactly what you had expected from this one plus two slits, right? Plus extra slit.
So, what's the difference between this thing in the middle?
Yeah.
So it's a mirror or some kind of device?
It's kind of what?
It's a lens or something?
It's not a lens. It's kind of a say a small device measuring the direction of the proton. The proton can move up and down in this thing. So if the electron comes this way, be attracted to here, kind of emit a flash here. If the electron goes this way, then you can emit a flash over here. So it indicates exactly whether it's going through upper or lower slit. So it's an indicator for which slit the electron goes through.
And that's an actual experiment that people did in the lab?
Yeah.
Not only this sort of experiment?
Right, yeah. And you can do the experiment, you'll see that the interference patterns is gone, it disappeared. Which is weird. It's like, so someone said, I think Feynman said this too, it's like by looking or by seeing this electron, the electron knows that you're seeing it, so it kind of destroys the interference patterns. Anyways, I think that's not the best way to think about it, but it is surprising nonetheless to have a monitoring device in the middle then the interference pattern is gone. And by the way, by making this less and less reliable, and this pattern will become more and more like interference pattern. So if something is precise mathematical going on, but just by looking at this experiment, it's quite puzzling. So 3 experiments, the single slit, double slit plus the monitor, of which way electron go through, they show some kind of weird microscopic quantum phenomena going on. And already at this point, we said the interference patterns calls out for explanation, namely to represent the system by a wave-like phenomenon, a wave function. And we postulate this wave function obeying a Schrödinger equation, which is linear in time, which kind of explains, in part at least, interference patterns. Now, the third one calls out for explanation as well. But let me just give you a brief partial explanation in terms of the mathematics wave function. So in this experiment, we still have, say, the wave function of the electron going through here, right? However, it's going to interact with the proton here, such that the wave function of the system is going to be divided into 2 parts. Now, to represent this, we think about the following. So when you have a 2-particle system, so E and P, where this is the position X, E, Y, E, and Z, E. Let's think about this 2-dimensional for now. So the location of the electron can be, in different X, Y coordinates, and proton too. But proton only has 1-dimensional variance, either up or down. So it's going to be represented by, say, this one thing. Let's say and Z, P. Okay. So 2 degrees of freedom for the electron, going either this way or this way. For proton, going on this way. Well, in reality, it's 3-dimensional, right? 3 here and 3 here. But the relevant information is only 2 numbers here, 1 number here. And the wave function of the system is no longer a function from R2 to C, but from R3 to C. So the wave function is going to be a function of XE, YE, and ZP. So for every way the electron-proton systems are arranged in space, there is a complex number. Right. So in this picture, we're going to have a 3-dimensional representation. Oh, okay. Another space here. Can you draw here? So what's happening here mathematically, we can briefly see as follows. You have a 3-dimensional configuration space. You have, say this XE, YE, and ZP. So X and Y, you can think about the 2 ways that the electron can move around, and Z is the 1 way that the proton can move around. Then you have a wave function, say, a plane wave coming in from here. Okay. Around the point of interaction between the proton and electron, we're going to have 2 ways the proton can be. One in which is going to be like this. One in which proton moves down. So here. So we go from 2-dimensional configuration space to 3-dimensional configuration space, in which there are going to be 2 distinct parts of the wave function spreading in this space. Now, so because these two parts of the wave function are kind of far away, there's not going to be the constructive or destructive interference between the two parts. Unlike this one, where when you have interaction, diffraction from here, they're going to have interference in the same plane. That's a crucial difference between this picture and this picture, when the interference pattern is lost here. And as you the reliability of that becomes lower, you can see this becoming closer. They'll be producing more interference. But given a perfectly reliable indicator, we're going to have two distinct parts of the wave function being non-interfering much with each other. Okay, so this is example I want to focus on now, because it illustrates the quantum measurement problem very nicely. Okay, so when we have the wave function of the system, say E1 plus say E2 and say phi of the monitor P. Okay. Put it this way. So the ready state of the monitor. So we know that if we have just say psi U1 going through the upper slip, then you're going to measure up. If you're going to go through the lower slip, you're going to measure down. So I'm going to write this down. Okay. Can you see here? Yeah. Okay. So the first fact we know is that suppose psi E up, and then we have say the waveform of the monitor is phi ready. And this is going to evolve into psi E up plus phi indicates up. Also, we know that if this is psi E down and phi ready, we're going to evolve into psi E down and phi indicates down as a reliable indicator, right? So when we combine these two together by the linearity of Schrodinger equation, we're going to have this one, so position between two parts. With phi ready, it's going to evolve to psi up and phi indicates up plus psi down and phi indicates down. Okay. So by the wave function evolving linearly by the Schrodinger equation, we have this result of the experiment. But that seems to be inconsistent with observation, in which we have a definite outcome of the experiment, namely it's either up or down. It indicates up from a flash here, or indicates down from a flash here. And this is not indicates up or indicates down. It is position of the two parts of the wave function. So what we have here is a simple illustration of the conflict between among three propositions. We have here the measurement problem. So if the wave function completely describes the physical system, then proposition 1 is the wave function is everything. The second, if the wave function always obeys the linear Schrodinger equation, and Schrodinger equation is always exact, universal, describe the phenomenon not only the moving parts, but also interaction between the system and a measuring device, then we have the second proposition. Schrodinger equation is universal and exact. But given these two propositions, we have the following prediction, namely that this will be the end result of the experiment, not particularly up indicator or down indicator. So These two are in conflict with the following third proposition, that outcomes of experiments are definite, either up, down, left, right. Okay. So the three propositions are in conflict, not bad. And the way to go is not to give up, say, classical logic or probability theory, but to think whether to give up any one of the three propositions. So in what remains, I'm going to briefly mention one strategy to solve the measurement problem. Namely,
so you have to pick a certain subset of this. Possibly it's empty set.
That's right, yeah, maybe nothing can solve the measurement problem. But we can still first try to see whether we can give up this one, or give up this one, or give up this one. So by the way, let me mention that if you give up this one, you have to add extra features, extra ontologies, particles or fields, what have you. And one particular version is called Boolean mechanics, given by De Broglie and Boole. So they have the wave function, and also you have particle locations too. You have extra particles with precise locations that move according to the wave function. The second strategy, if you give up the universality or exactness of Schrödinger equation, you might run into something called the GRW formalism of quantum mechanics. It's a different way, different theory of quantum mechanics. I mean, this one is different too, but this one modifies the Schrödinger equation. So the Schrödinger equation is not always exact. It should be given up by something like a stochastic evolution with spontaneous collapses. The third one is the very infamous picture of Everett. We deny that there's no definite outcome of experiments. Maybe all of them are equally real in some sense. The many worlds interpretation, in which say not only there's a world in which you see it is up, but also there's a world in which you see it is down. So three propositions points out to three ways to deny to give up something kind of seem to be standard orthodoxy. And we'll focus on this one first. Broglie-Bohle formalism.
What about the orthodox approach, the Copenhagen?
Yeah, so it's hard to pin down exactly what Copenhagen says, because the Copenhagen interpretation is kind of a collection of sayings of Bohr and Heisenberg, Pauli, and others. It's not always consistent. So one way to understand this, I think, is that there's no macroscopic world. So it is foolish and it is hopeless to insist on an exact picture of the world at the fundamental level. So we can talk about tables and chairs, but don't talk about the location of particles.
So
if you do talk about them, you have
to talk about it.
Yeah. So yeah, but there's also variations in which you might have Copenhagen with a collapse postulate, some kind of observer-induced collapses, right? So there are many versions of Copenhagen, and it's not very clear what they mean exactly. Right. But sometimes I think they want to say the Schrödinger equation is not always exact. So you have collapses. One's kind of measure the device by observing the electron, say, in the third experiment, or say on the screen. Okay. So the Boolean mechanics. So Boole theory suggests that maybe, well, let's try first that if waveform is not everything. It seems like when we have wave phenomena, interference and appearing or disappearing, we also have particle phenomena. You have a particle landing here. You have a flash at this landing here, right? A flash here, flash here. Even in this case, we have this curve is not like something we observe directly, but it's only by accumulating flashes on the screen. How many flashes are here? We have more here, so it's a higher curve here. So the flash on the screen.
Even in the first case.
Yeah, in the first place, you have a flash on the screen. It's more direct. It's just that the wave phenomenon is not so obvious there. When you have wave phenomena, you also have particle phenomena. It seems like maybe you need both. You have the wave function doing that thing by the Schrödinger equation, interfering constructively or destructively giving interference patterns, or giving you, say, two parts of the wave functions. You also have particles doing nothing, moving along somehow, and landing on the screen. And the idea is that you, the wave function is not everything. Okay. So you have this wave function describing the wave phenomena, but also the particle Q. So particles in pre-specified locations, say Q1 and Q2 and up to Qn in the particle system. So Q1 is the xy is equivalent of the first particle, Q2 is the xy is equivalent of the second particle, and so on. And this together is called a configuration, the way that particles are arranged in space. And there's going to be a precise equation of how the configuration of the particles change. And that's given by what is called a guidance equation. So, yeah, let me just write down the guidance equation. dq constant, right? Okay. So sorry. So this means the velocity of the cake particle is given by some constant in front and some imaginary part operation. Basically, the most important thing is here, the gradient of the wave function. So the thought is this. If you want to have a simple, with the most natural velocity of particles, velocity equation of particles, then you can get it from the wave function. But the wave function is the scalar field, say in complex case, scalar field on configuration space. And the easiest way to get a velocity field from the scalar function is by taking the gradient of the scalar field, which means suppose we have a scalar field like this, then the gradient will be pointing to the steepest way of ascent, right? And this means that with velocity field, we have a vector field arising from the scalar field by taking the gradient. But also we want to have basically that wave functions differing by a constant over a phase, giving the same velocity field. So when we have a gradient of psi, we divide it by psi itself, which will cancel out any constant factor of the wave function. But this could be in general a complex number, so we take the imaginary part, we give it a real number, so real velocity field, with some constant in front. Okay, and that's the basic idea behind the guidance equation. And then there's other arguments about.
Your explanation doesn't justify why you take the imaginary part. Why don't you just take the real part?
Yeah. So so there are two ways to do it: either taking the imaginary part or real parts. So I think taking the imaginary part identified by the choice of some symmetries,
No, that's how you get a continuity equation.
Right,
I see. You don't get it.
I see.
No, right, he's right. Symmetry, but it's a time reversal symmetry.
I see, yeah. Right, so t to minus t. Right. And the constants you justify by taking symmetry argument of boosts and so on. So there are natural arguments for why the form of velocity equation is given by this. But in any case, so suppose this is a well-defined physical theory, mathematical physics theory. You have particles and you have wave function. Wave function evolved by the Schrödinger equation. Particles evolved by what is called the guidance equation, which is basically taking the gradient of the wave function in configuration space. And this two, the claim is that this two will be sufficient to explain all of this phenomena. Once you do the calculation of Hamiltonian, plugging Schrödinger equation, and calculating the vector field by the guidance equation. And in fact, you have done calculations of, say, simple models where you can actually do the calculation of the velocity fields. And it turns out, exactly, most of the particles will land in this part, this part, this part, this part, and almost none will land in this part. And distribution will exactly be like given by magnitude square of the wave function. That's assuming additional hypothesis that is, say, given initial wave function of this form, say psi, and this indicates, say, amplitude of the wave function. Most particles, most initial, okay. Right. So the particles will be given distribution, given by psi naught squared. So the probability of say, finding the particle here will be given by the modulus square of the wave function. So with this assumption of the two equations, you can derive that the frequencies of, say, particles landing on the screen will be given by exactly the empirical distribution and conforming with the Bohr rule of quantum mechanics. Okay, so one thing we can do is to think through more carefully in this case. Let's see. So, yeah, in this case, how do you solve the measurement problem? So in this case, where you have the with monitoring device added in, right, and you have a disappearance of interference patterns, and you only observe definite outcomes, so you don't get this by just a quantum mechanical plus Schrodinger equation. What you have is that particles will be added to the wave, and they will follow the current of the wave function. And some of them, initial ones, will go this way, and some of them will go this way, given different initial location of particles. If you go up this way, you will show, first of all, you will show that this one will be indicating up, and the electron will show up in this part of the screen. If it goes down this way, then this one indicates down, the electron will show up on this part of the screen. So the interference is gone because the guiding wave here doesn't have interference from the other parts. And definite outcomes arises because there's an extra ingredient in theory, namely particles with locations. They always obey one precise trajectory. So given enough initial particles, you can always exactly find there's always going to be definite outcomes of experiment plus a distribution like this. Right. So and this can be made more vivid by thinking about even bigger macroscopic systems like Schrodinger's cat, and even human beings can be entangled with the environment, with the quantum system. So I think that's about it in the talk. Right. Let me stop here to see if there are any questions or clarification. Thank you.
So which of the three choices is your favorite?
So my credence is this. Um, 5%, 20%, and I would say 70%. And the third one is maybe something else. The fourth one is something else, but mostly is if I were to bet, I would probably bet on this one. Because, first of all, so between this one and this one, so between JW and Bohm, only Bohm will produce the prediction of quantum mechanics whenever quantum mechanics make a prediction, and JW will deviate from that. And a lot of versions of JW have been falsified already by experiments. My low credence in this one is because that it's very hard to make sense of the probability of quantum mechanics if all the outcomes are actual. And the way to make sense of that by average and other people like David Deutsch and David Wallace seems quite arbitrary. Unlike in this one, the probability can be given by simple arguments, dynamics, and so on. So That's why I think this one is, first of all, empirically adequate and also most natural.
So in the bomb, the body it's not deterministic.
So both bone mechanics and everything quantum mechanics are deterministic.
So Einstein would have been happy with it of that?
You would think,
Yeah.
but Einstein in private letters was not so happy. When he talked with Spock himself, he found that this interpretation to be too cheap in some way.
Oh, like it.
But I think it's actually because he was expecting a local theory of quantum mechanics.
Oh, so you were unhappy for different reasons.
Right, right. He wants this to be local, but this one is explicitly non-local because here you have the velocity of one particle depends on the velocity, the position of all the particles. So you can have far away things make a difference to where it goes about this particle. Right. But unfortunately for Einstein, the goal to look for local theory is impossible, given Bell's theory, which was published after he died. Right.
Oh, so maybe in retrospect we would have a proof of it.
Yeah, maybe he would have liked this better if he knew about Bell's theory.
What cell is ranking distribution?
Oh,
100% for the first
I
one?
would say, I would give the second one maybe 2%. It's ad hoc.
Right. Yeah.
And the third one maybe 0%. I mean, I think they're all, 2 and 3, just based on this. You take the mistake that was made of thinking the wave function's everything, which is one of the stupidest thoughts anybody could ever have, and you try to put lipstick on that pig. You're not really biting the bullet, whereas you just say the obvious thing, particles have positions whether you look or not. Then you got one.
Yeah.
And the other predictions for quantum mechanics can be done.
Right. So the nice paper is by Shelley and co-authors, and they are going to show in a very rigorous physical mechanical method that given the hypothesis that particle distribution be like this, it follows that small subsystems would display the kind of patterns predicted by quantum mechanics, and there's going to be, in principle, unknowability about the location of the particles beyond what's predicted by the wave function distribution.
Yeah, and it's not so much that you assume particles are distributed like
Right,
that.
right, right.
Because if you think about it, you don't even know what you mean by saying the probability distribution
Right.
of the configuration of the universe is that.
Yeah.
So you have to make sense of what that even would mean.
Right, right, right. So a large part of that is making sense of that, and typicality statements involved in that too. What's nice about this theory is that it disproves refutes so many arguments about impossibility. So findings that it's impossible to understand double-slit experiment in a classical way. If you mean by classical, mean there's some definite particles going through the slits, then there is one, namely this. And refutes the arguments that it is impossible to think about quantum mechanics in a consistent way, or in a single world, or without collapse. Then we have also proof that this exists, therefore it is possible. Of course, what is left over is to do this for more advanced systems and for particle creation and annihilation, quantum field theories, and for quantum gravity in the end. I think it's very promising. It's just that there's so few people working on this that we haven't made a lot of progress beyond, say, realized models.
And there have to be so few people working on it, because you cannot tell physics students to work on it because they don't get a job.
Yeah.
Right. Yeah.
But some people still work on it, like you and Eddie.
Philosophy of physics can work on it.
Yeah.
Right. Yeah.
Luckily we have philosophers.
Yeah.
Any questions? Thanks for a beautiful talk.